Hello, everyone. We are gonna continue. Let's welcome Steven to talk about the supervised program problem solving flow.
Hi, everyone. Hello, Steven here. So I will talk about typical workflow for solving a supervised machine learning problem. So solving a supervised machine learning problem will usually involve 5 steps. The first one is data representation, and the second one is problem formulation, and the third one is hypothesis construction, and the fourth one is matches for evaluation, and the fifth one is tools or models. So, okay, so the problem is that we want to know how much time, how does the sleeping time relate to our midterm mark? So we need we need data to do that. So we can ask your friend, do a survey, do whatever, just collect the data. So, but sometimes collecting data could be really, really hard. So let's assume we already collect the data. So what we have is your friend's sleeping data. So we just denote it as X, and we have their midterm mark. We denote them as a Y. So we just write them into 2 vectors. So we have vector X and vector Y. So what if we want to investigate other factor, how other factor affect our midterm mark, such as time spent on dating, playing video games, whatever, clubbing. So what we do is we append extra columns to our X vector. So what we have is matrix instead of a vector. So what it is that each column of that matrix is what we call features. What it is the time spent, so on sleeping or playing video game, whatever. And each row is representing 1 data point. In this case, might be one of your friends' data. So in this case, we have n friend and n features. So let's move on to problem formulation. So in this case, we have time, we have mark, so the data is labeled. So in this case, is obviously a supervised learning problem. So supervised learning problem is basically a mapping from input to output, or X to Y, or in this case, time to the midterm mark. So we can write them as Y goes to a function of X. So then let's move on to hypothesis construction. So first, we want to do some data analysis first. We just say plot that out. The x-axis is the time spent on sleeping, and the y-axis is the midterm mark. So we plot it out. It looks like a linear relation, right? So what we do, our hypothesis here is just like they are linear relation between the sleeping time and the midterm mark. But usually we have we have high dimensional data, because remember the case where we want to investigate how does other time span affect our midterm mark. In this case, it's really hard to visualize our data, because we can really visualize data more than 3 dimensions, right? So what we usually do is try and error, just try other hypotheses, see which one works better. Or we can use some sort of dimensionality reduction method to sort of reduce the dimension, so we can just visualize them to guess what's the relation between the input and output. So then we move to matches for evaluation. So there is the plot that I just showed. It's the same. So we want to find, because we guess the hypothesis here is a linear relation. So we want to find a line that represents our data. So we just randomly draw a line. Is this line really good to represent our data? Okay. What about that one? Worse? Right? So a little bit better. What about that one? Much better than the previous 2. right? So how do we know which one is better? Any guess?
Yeah.
Yeah. So yeah, we just need to find a matches to evaluate it, right? What you just described. It's just you can define your sort of your matches like mathematically, right? So in this case, what we do is we define a loss function. It is mean square error. So what it does is that's the formula. MSE equals to whatever. So the first y there is real mark that we collect, and the other y tilde there, I'm not sure if you can see the tilde. The y tilde there is the predicted data, the predicted mark. So what it does is the red line there is our sort of hypothesis, and then so what we do is we get the distance between the data point and the line. The vertical distance is that whatever it is the y minus y tilde. So we get that distance and then square them, and then we just do the same thing for all data point, and then we just
Why would we square them?
Okay, so that's a good question. So if we don't square them, you would just say, let's say we have like a horizontal line. It's a flat line. Okay, you have that data point in the left part. Your y minus y tilde is positive, and in the other side is negative. It cancels out, right? Or you can do like you can put a absolute value, right, to make it to like solve this cancel out problem. But in this case, the cost function is not differentiable. We will talk about why we need differentiable cost function later. Okay. So any question for the MSE? You guys know what's MSE then? You just like square them and then add all together, and then just divide by how many data you have. Okay. So let's move on to model or tools. What we have, the first model that we want to talk about is linear regression. What linear regression is that first we have a line y equals to m plus b, mx plus b. Pretty simple, right? High school stuff. So m is slope here, and then b is the y-intercept. So the m and b define a line. So y here is a mark, x here is a time. So y and x is given. So we just want to find the best sort of the m and b for the best line. So the best line is defined by the MSE, right? Defined by the metrics. So how do we find the m and b? We fill out the algorithm for gradient descent. So because MSE define how good the line is, the less the cost function, the better the line. So MSE here, this is a function. We can write the y tilde as a mx plus b. And since y and x is given, so the variable here is only m and b. So we can write MSE as a function of m and b. Usually we write the m and b as a theta, as a parameter of that model, because the model is defined by the parameter. It's a m and b, right? So by minimizing the loss function, we can find the best line, such that we can find the best line. So we just find m and b. Okay. Any questions? No. Okay. Good. So gradient descent. The plot here. First we make the things simple. So we just ignore the b. We just talk about n. Right now we just m hypothesis y equals to mx, no b. Okay. So the y-axis is n, and the x-axis is n. The y-axis is the loss function. So the first step is we randomly initialize our weight, our parameter, in this case n, and then we can calculate the predicted y. And then once we have the predicted y, we calculate the MSE. So the MSE is a little red dot here. Okay. And next step is we calculate the derivative of MSE with respect to n. So it's the green line there. So we will, because the derivative is really, derivative means by moving the n a little bit, like how much it can affect the MSE. So what we can do is we can update our n to minimize our loss function. So what we're actually doing is to update our n. So we update our n by moving the n along the negative direction of our gradient. Okay. So by how much? The how much is defined by the alpha there. The alpha is called learning rate. Okay. And then we calculate the predicted y again, and then calculate MSE again, and then we have next point, and then we do the whole process again, and again. As you can see, our n, our loss function is actually decreasing by updating our n. Okay, so let's get back to the situation where we have m and b. Okay, we do the same thing. We calculate the predicted y, and then we calculate MSE. But instead of calculating, we also calculate the derivative of MSE with respect to n, but we also calculate with respect to b. But in this case, it's a partial derivative. So if we write those two partial derivatives in a vector form, it's called gradient. So this is why it calls gradient descent. Okay, and then we update b as well as how we do for the n. So we just update it. So this is how the gradient descent works. So because you can always add an other partial derivative to it. So the gradient descent, this algorithm can generalize to whatever dimension you want to have. Okay. So this is what happens if you apply the gradient descent. So first we randomly initialize our m and b. So we have like that line, right? And then throughout the iterations, and then the algorithm will update m and b. So you have that perfect line there. Okay, so this is another model to solve this problem, which is called neural network. Okay, have anyone here not heard about neural network before? Anyone? Everyone heard that before, right? Okay.
I know about neural network.
Okay, so you have a question.
About
Yeah.
that learning rate for M and B would be the same or not?
So for that one, you can define as same, or you can define not the same. This really depends on your decision. And like could be a vector, right? Yeah.
So how do you choose your learning rate?
But your learning rate. So tuning your learning rate is a good question. So usually you try to do a research for your learning rate. Because let's say if your learning rate is too large, what happens? You care if you want to move down here. If your point is here, what you have is you jump right here because your learning rate is too large, right? So it really depends on, you can do the learning rate you can change throughout the gradient descent process. You can like say have a decaying learning rate. You could say before we want to have a large learning rate, so we just like converge really fast. But when you reach the bottom part, you want to like have a smaller learning rate so that you won't like jump back and forth, right? So we can like, it's something called learning rate scheduling. You can search if you want. There's many algorithms to like any sort of strategy to change that learning rate throughout the whole process. Okay. Any questions? Anyone? Good. So let's talk about the neural network. So anyone knows what is neural network? Okay, a few. Good. Okay, let's talk about neuron first. So this is a drawing of a biological neuron. So the neuron has basically two parts. So one is cell body, and the other part is action. Cell body, this part, as in this part. Okay. So the cell body has many dendrites. The dendrites is connected to other neuron. So the other neuron will send sort of impulse or signal to this neuron through the dendrites. Okay. So the cell body is the neuron itself. The cell body will collect all the received impulse and then check if this like sort of threshold here. It will check if the impulse exceeds the threshold or not. If it is, it just send that impulse or signal to the next neuron through the action. Okay, this is the biological neuron. How the biological neuron works. As a programmer, what we mostly do is just copy and paste. So we just want to copy that biological idea into a computer. So the left-hand side is just what we have in the previous slides, and the right-hand side is the neuron in neural network. Okay, what we have is the X. We still have X0, X1, X2, Xn, whatever. So X is the impulse or signal from the previous neuron. Okay, and then for each X, we have W. This is the weight. The core response is the weight for the specific X. Okay, basically for each X, it has its own W. Okay, so we just sum all the W, X together, and then plus a B. The B here is called bias. So right now it looks like it's a sort of like a linear regression formula because you have sort of mx plus b, but n here is w. Okay. So and then this part just simulate the cell body itself, and then in terms of the threshold that we have in a biological neuron, we use something called activation function to sort of mimic this behavior. So the activation function is something that we apply upon the linear combination of that incoming signal and plus the bias. So the activation function is usually nonlinear. Yeah. So what is neural network? The neural network, the term neural network itself is pretty straightforward. And then, so neural network is network with neurons. So this is a drawing of a really simple neural network. So the sort of circle there, just representing one neuron. Okay. The first column is called input neuron. What it sends out as a signal is the input. In this case, sleeping time, clubbing time, playing video time, whatever. So, and then the second layer is the hidden layer, we call it hidden layer. In this case, we have two hidden layers, and then the final layer is what we call output layers. What it is just the output. In this case, we have only midterm marks, so we have only one neuron in the output layer instead of two. So, what neural networks work is that first the input layers send out a signal, which is the input, to the second layer, and then the second layer do the calculation, and then send the signal to the last layer, and then so on and so forth. And then for the output layer, we have what we want, the output. Any questions so far? Oh, good? Good.
Quick question.
Yeah.
So what happens at each hidden layer?
What happened to each hidden layer?
What do you do at the hidden layers?
The hidden layer is sort of some signal inside. is how to interpret what is inside is an active research field right now. So many people try to like interpret what is inside. So it's an active research field. Okay. Any other questions? Good. Good. So why neural network can solve our problem? There's a theory called universal approximation theory. What it says is that a neural network with a single hidden layer containing a finite number of neurons can approximate any smooth function. It's really powerful. So it can. The hypothesis here is a straight line. So straight line is a smooth function. So it's a smooth function. So in theory, our neural net can approximate that line function. In fact, look at that small mean out there. It can simulate the sine, cosine, or even the graph function on the really right corner, that graph function. So neural net is really powerful. So in neural network, what we have is W for each neuron. What we have is W and B. So W and B defines a neuron. Okay, similar to the linear regression, right? So W and B is really the parameter of our neurons, because neural network is a combination of a whole bunch of neurons. So basically, the W and B for each neurons define the neural network, right? And also the structure of that neural network. How many hidden layers do you have, etc., etc. So how do we learn the W and B we just talked about? Same stuff. We use gradient descent. That's the gradient descent we had before for linear regression. But instead of M and B, we have W and B, right? And then we have many. So y is equal to f of x still, but given a theta. Theta is the parameter. Okay. So we do the same iteration and also update the parameter as what we do in a linear regression. So because the activation function is, do you know that, have anyone here know what is convex function? Two? Good enough. So basically convex function, in short, it means for a function, if you find a local minima, it means the global minima. Basically, what is convex function? It's a function looks something like. Basically, what's convex function? This convex function. Simple as that. So you can prove our linear regression model before is the loss function of the linear regression model that we had before is a convex function. So no matter where we initialize our weight, we always go to the local minima, which is the global minima in this case. So we find the best line that we can get for that specific model. Okay, but for neural net, because we have activation function, which usually is not linear, so it's usually the cost function is usually not a convex function, which means it has many local minima. So for example, in this graph, you have like two sort of minima. One is one is here, one is there. But that one is the global minima. So if you need to have the theta as sort of, I'm not sure if you can see, it's like 10, 25 right here to have that best model that you can get, right? That's a really, it's a problem. What if we initialize our weight such that our start point is at 8 right here, 8. 8, can you see that? 8 point right there. So if we initialize that our parameter such that the first point is at A, then if you want a gradient descent, you just start into that local minima, and then we find a global minima because we don't know what it looks like. So, but in practice, finding a local minima is usually good enough to have the really good performance. Yeah. So it's a problem, but in practice, we don't really consider that much. And yeah, that's pretty much it. Any questions so far? Oh, good, good. So to just sum up, we just talk about what's machine learning and really basic concept. And also we talk about the 3 types of machine learning. And finally, we just walk through the sort of workflow for solving a supervised machine learning problem. So, as Yishan mentioned, we have the next MIST101++ is. I don't know that. Okay. So next event that from back
and yes, summary shows our reinforcement learning extensively. You will be given a specific and in-depth talk on reinforcement learning on November 19th. So if you guys are interested and you guys want to have more about machine learning, definitely come to check out our next workshop. And I'm so sorry that I'm late today. Apparently that the TDC guys don't know machine learning, so they're algorithm to like manage the street lights are so shit, and I keep getting traffic jams. So, but anyway, hope you guys have fun today, and do follow us on Facebook, on Beach, and all the social medias, and keep track of what we are on to with more events coming up, speaker events, more MIST101 in our project. So, thank you everyone for coming. Thank you again. So, hope to see you next time. Don't suggest a feedback.